All right, line number P3, learning task 4, we're going to take a look at autotransformer connections. And we're not talking about single phase, we're still obviously going to be talking about three-phase autotransformers. That being said, we're going to start with just some real basic autotransformer theory. Excuse me. First part of the autotransformer over here is just, our first part of the theory is just the fact that on an autotransformer, we no longer have got side-to-side isolation. Our autotransformers have got what we refer to as a common part of the winding. That is going to be used both to go and deliver power from and to the primary, take that current back and forth, as well as we are going to go and have the current that is flowing through the secondary, that is going to go through that common part of the winding. There is going to be another part of the winding just up top over here. This is just going to be attached to the primary winding, always the longer because there's more turns, number of turns in the primary. There will always be a section that is only going to be associated with the high voltage side. And in this case over here, they're showing us a high voltage going down to a low voltage over here. We can tell that just from the number of turns that are there. They are only going to transform a small amount of the current. We're going to go and have some current that is going to be conducted directly through. In other words, we're going to have a small amount of current that is going to go and travel through from here out to my loads and then come back in and travel through like that over there. And we're going to have the rest that is going to be placed up through what we see over here, this common part of the winding. How it works is that we're going to go and have energization of our coils. Those energization of the coils is going to go and create magnetic flux. That magnetic flux is going to enter the core, that's what these two lines represent, and is then going to get transferred back to the next section over here. So it's working still through the same principles of electromagnetism. We are fluxing up that core and then just dumping that flux in, cutting across the conductors on the other part of the transformer to go and create values of voltage. Because we have got shared windings, they're going to go and require less actual windings themselves to go and make. There's going to be less copper that's going to be associated with less copper. They're also going to go and have less steel for the core itself, which means that overall it's going to be a cheaper transformer to go and manufacture. It's going to be smaller because I don't have to go and completely isolate these things. And I'm going to go and have a higher efficiency because I have got less core. And as soon as I get less core, I've got less area for all of my shred losses, skin effect, hysteresis, radiation, eddy currents, and dielectric losses. And last of all, I'm going to go and have a lower percent impedance. There's less copper in there, therefore there's going to be less resistance or impedance. And if there's less impedance, I'm going to go and have better voltage regulation. The more resistance there is, the more that my IR drop would increase across the transformer, and the lower my voltage would sag. But because there's less resistance, I'm going to go and have less voltage drop. So there's a lot of net benefits to them, but there are some disadvantages. The main disadvantage is going to be that low percent Z, that impedance. And because I've got a low percent Z, I'm going to go and get a large amount of fault current. You should remember how to calculate fault current from second year, and your fault current is going to go and be where you're going to go and take your secondary current, so I secondary, and you're going to divide that by your, oh, sorry, that's a root there, I'm so used to, you're going to divide that by your percent impedance. And if that percent impedance is small, the resulting number that's going to come out of here, your fault current, amps under fault, would be therefore quite large. Because of that, there are actually going to be some situations where they're going to go and put impedances ahead, line reactors and stuff like that, particularly when they're working with, dangerous high voltages, etc. The other issue is the fact that we have got common issues over here because we don't have that air gapping from one side to the other. Any sort of weird currents that we're getting, disturbances that are going to happen on our line, harmonics and things like that, are going to be able to get transferred all the way through to my load. Normally transformers are really good at filtering them because a transformer is simply two inductors, and two inductors is just going to go and act as a really good filter, cut off a lot of these really spiky, dirty little bits of waveform. But now we're able to conduct them straight across. So we do get more issues across like that. And last of all, if I have any sort of a fault in my autotransformer, particularly this over here where I'm going to go and have a break, what is going to go and happen is I'm no longer going to go and have transformer action. Then I'm going to go and get actually just a gapping over here. And this section that's over here is no longer going to act as a transformer. It's going to go and act as a reactor or a choke, which means it's going to slow down any rises or falls, but it is not going to actually stop them. So over here, if I had a good working transformer, we'll just erase that there. If I had a good working transformer, I've got 120 kV primary, and I've got 120 volts that I should have across here when this thing is going to be working. And so working normally as a transformer, I'm going to go and have a primary line current. We'll just draw it going through like this. That is going to be going through like that. And it's going to be an I line that's going to be tiny. Okay, we'll just write that out as being tiny because it's 120,000 volts over here. A tiny amount of line current. Well, what happens with that line current is every time that that line goes through a single one of these windings, it is going to be creating flux, and all of that flux is going to be dumping into this core. So we're creating all this flux through all of these common windings, and then what happens is energy cannot be created or destroyed. It can simply be transformed. All of that flux is then going to go and get dumped back in over here, but across very few windings, which means that we're going to go and get a large amount of current. So what we would normally have under ideal operation is that I'm going to go and have a low value of voltage coming out here, but I'm going to go and have a really large value of current that I would be able to go and put out from here, just due to the transformer action itself. This would be the way it would normally operate. I'm going to go and have counter EMFs in here that are going to go and oppose the flux that is inside here. And so this whole system works inside of balance at that point. But as soon as we go into a break over here, all of that shuts down. Now what we're going to go and have is we have got this 120,000 volts. And basically, as far as my 120,000 volts, it just sees that it's got a reactor ahead of itself, and then it goes to its load. So 120 kV, and over here is my load. Really now it's just acting as if it's traveling straight through a reactor, which would be these windings right over here, and then going out to the load. So it's going to be a slight bit less than 120,000 volts, but it's really not going to make a difference because 120,000 volts over something rated for $120 is going to result in instantaneous destruction of that. So it gets really, really dangerous. Because it's so dangerous, and because it's going to, if it will fail violently. We don't want to place these inside. They're normally going to be placed outside. And we're not usually going to use auto transformers for massive jumps down. Over here, we're going from 120,000 down to 120. That would be 1,000 to 1 transformation ratio, which would be highly dangerous. Normally, we are going to go and limit it to generally no more than a 3 to 1 transformation ratio. There's another issue that can happen with these as well with auto transformers, and that's where if I'm using it to go and do a small step over here. And so right now I've got a primary side 240 volt, a secondary that I'm going down to 208, and normally I'm going to go and have my windings connected across here, which means that once again I'm going to go and have current through my primary that is going to be fluxing up that core, transferring flux into the core, and then that flux is going to get divided across all of these, and we're going to go and have a counter EMF that's going to get built up in our secondary, and we're going to deliver proper rated line voltage over here. Normally that would be 208. It would work in tension because, well, everything is complete, but as soon as we lose this over here, we are going to go and lose all of this normal operation over here. But what we aren't going to lose is we aren't going to lose the fact that we are still going to be running current through here, out to our load, going through our load, and then coming back in over here. And what that's going to do is we are going to go and have a massive amount of flux that's going to be developed through here because we're no longer getting a countering flux from the secondary side. Once again, if you're having trouble with all of the fluxes, I'm working off of the fact that you've passed second year, and so you must understand it. But if you don't remember how transformers set up flux in the primary, and the fact that, you know, I've got counter EMF in the primary and my secondary voltage is in phase with the counter EMF in the primary, you got to go back to your second year books. Okay, this is third year, we can't teach it again, but we rely on you to actually understand that. Okay, so we're going to go and have no counter EMF that's going to be produced in the rest of these windings, which means that what's going to happen is we're going to go and get this saturation of the core. So the core is going to get filled completely with our flux, and we're going to go and end up with this. You should recognize this. This is the hysteresis curve, or as I prefer to call it, the hysteresis crow. And that thing will peck your eyeballs out if you go and screw it up. Because what the hysteresis curve is it is showing that we are going to have, we got a BH graph that centers across there. And as we go and increase the amount of magnetization that's going to be across here, we're going to go and see an increase in the amount of flux until eventually the flux tops off. And then that's going to be it. And then we drop our magnetization in the opposite direction. So because it's AC, the magnetization changes direction. And so then we are going to go and drop the amount of flux. And then we're going to build rapidly in the opposite direction. It kind of goes back and forth like this. But what happens is we see that it's a relatively flat line across the top here, which means that there's a sudden change. Which means that basically it's like loading up a very large spring. So we're going to go and load this thing with flux, 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 flux. And then all of a sudden, as soon as our waveform crosses back over the opposite way and our magnetization goes this way, we're going to rapidly dump that out. Because we're rapidly dumping out all of that flux, it is going to go and induce a very large value of voltage. This is how electrical igniters work, is we go and take a coil, we put current through it, and then we drop that current really rapidly. Think about a barbecue or a stove or something like that, that snapping noise is a small circuit that is just opening and closing really, really rapidly and creating that spark across it. Over here, you would end up with a very large spark. You'd induce a ridiculously large value of voltage because inductors want to go and maintain the flow of current, which means that if there's supposed to be current flowing through here, they're going to go and create a really large value of voltage to try and get across that air gap, which might be in the millions of ohms over here. And in order to go and maintain, 1 or 2 amps through a million ohms of resistance, it's going to have to go and put out 1 or 2 million of voltage. This is really dangerous for obviously anybody that's going to be around there. Not a large amount of current, but it's still going to be a ridiculously high value of voltage, which leads to injury. Okay, that's our dangers off of these ones. So stay away from, these if you can possibly do so. High transformation ratios are going to be really bad. On low transformation ratios where you make a poor connection or the actual transformer itself goes and fails, you're going to go and run into issues then from the hysteresis crow. Okay? All right, the Y connection for a Y-connected autotransformer. Y connection is a very common autotransformer connection. This Y connection is used in 2 main applications. First of all, it's used for reduced voltage starting, or what we sometimes refer to as compensating starting on larger motors, where we are going to go and have multiple taps that we can go across. We might start down here and move our way all the way up so that we can go and slowly increase the voltage to a motor to limit the amount of inrush. The other way that's going to be used is we are going to go and use this thing inside of high voltage transmission lines where the line's coming in on these and then it's going to be coming out on these X's over here, and we can go and move up a tap or we can move down a tap depending upon what the actual line value is like. So we can use it to go and compensate for any loading on the line or any disturbances that we have. What it is not very useful for is it's not very useful for supplying single phase loads, and we want to be really careful about what we use these Y autotransformers for. If you have got a bunch of single phase loads, so if you connect this thing to a neutral over here, and you go and take a whole pile of single phase loads just out of this phase over here, what's going to go and happen is we're going to go and have a lot of current. And if I get a lot of current, what I'm going to go and get is the current is going to travel through these windings, which are physical. They're made out of copper, which means that they have got resistance, which means that I've now got I and R, and I times R is equal to V, or volts. So what we would see, because we've got a large amount of single phase load going through that one, is that we would start to go and get a voltage drop that we would start to see across here. And as a result now, all of a sudden, all of my phasers are going to go weird, because I'm going to go and have 2 lines that are going to have, voltages, phase voltages that are going to be larger. And then I'm going to have one where it's going to be a phase voltage that is going to be smaller, because I have dropped that value of voltage through the fact that I've got a large amount of single phase current. And this is now going to go and lead to a pile of different problems inside of here. First of all, my line-to-line values of voltage are going to be unequal across here. Secondly, my neutral current is not going to completely cancel out. I'm going to have actual neutral current, and it's going to be out of phase as well. So we're going to go and get just a pile of different small issues with it. We're not going to go and use this thing where we know that we're going to be intentionally supplying single phase loads. We got another transformer coming up for that. We'll take a look at that one a little bit later. Let's look at this thing as far as actual connection for motors, though. One of the things that we note about this is that I can go and use my transformer formulas, NP over NS, number of turns in the primary over the number of turns in the secondary, is equal to my EP over top of ES that I'm going to go and have. That's going to go and show me where I'm going to be able to take up higher, smaller amounts of voltage. Let's go and say that we've got across here on our high voltage side from line to line, we have got a value of 600 volts. Okay. If I've got 600 volts going across there, that means that my phase voltage is 347 volts that I'm going to go and have across from here to here. And then I'm going to be tapping out of that 347 volts and feeding out to my actual load. We'll go draw a motor over here and we'll just connect a couple of lines across to this thing. 347 volts, that's going to be placed over here, and now I'm going to be able to go and tap inside of here. If I move this tap all the way up to here, I would be seeing full line value of voltage because the number of turns on the primary would be all of these, and the number of turns on the secondary would be all of these. In fact, I could just look at it as if I'm conducting that directly across over there. In reality, we'd only have a small amount of magnetizing current. But as I move down from the top point over here, I'm going to be dropping the amount of voltage on the outside on this motor load that I'm going to go and have over here. So what I can do is I can go and have a sliding set of taps that I can start all the way down over here, and I'm going to start on all three lines down over there. And that means that when I initially close in on my motor, because I'm only seeing a small amount of voltage, I get a small amount of inrush. I get less torque as well, because the torque is directly related to the amount of voltage that's going to be across it. But I'm going to go and have a smaller inrush, and I can let this motor kind of start winding up. And then as the motor winds up, I'm going to be moving my taps, tick, 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 on all three of these at the same time, usually done just through a slide or something like that. And then it is going to go and ramp up the voltage to the motor, allowing me to do a simple start that is not going to go and disturb the rest of my electrical system that much. It is my most efficient type of three-phase auto-transformer connection as well, especially by the time that I move all the way up to the top tap over here. At that point, it would be direct conduction across, and all I would really be seeing is going to be a very small amount of magnetizing current that's going to cancel itself out. But it does have some issues if I have got poor grounding. Okay, you're going to be in charge of your grounding. You got to make sure you do that properly. If you don't ground the neutrals off of these ones, you're going to go and get problems with your third harmonics. Harmonics are just going to be multiples of our 60 hertz. So a third harmonic is going to be 3 times 60 or 180 hertz waveform. And what it does is it goes and gives us this really kind of a humpy sort of line that we end up with that can cause a lot of problems for our voltage, because it's going to have a really fast leading in edge, but then it's going to have a slow dropping out edge, and it never really properly peaks correctly. So we want to try and avoid that. As soon as we do get these harmonic voltages, we also start to lose equipment. It just damages the equipment because it cannot withstand that sudden sharp, shock to it. Instead of having a waveform that looks like this, let me just draw one of these. That's what our waveform should go and look like. Our third harmonic voltage is going to go and cause it to lead higher. Then it's going to kind of drop across the peak over there. And then it is going to go and drop faster and then lead higher in the bottom, drop and drop faster. And it's really these lines that are really tough on my equipment, as well as the fact that up in the top over here get a little wobble and up down, and so we're going to get a fast dump and then a rise again of our fluxes. It just causes issues in the long term. What you can do in some cases, we're going to go and have a specialized set of windings called tertiary, or like extra windings that are going to allow us to go and cancel some of that out. We're not going to go into them, but they do exist for some of these applications where it's critical that you use this transformer, but you also have got those third harmonics that are already online. Okay, let's take a look at our next one, which is going to be the Delta Autotransformer. All right, the Delta Autotransformer over here is going to be limited in its amount of transformation. We're never going to be able to achieve more than a 1:2 or a 2:1 transformation ratio. And that's just built off of the fact that if we take a look at it, I'm going to be ultimately drawing a triangle across 3 sections inside here. If I rotate that triangle through, if I get a triangle going through from here to here to here, I am going to go and be at 50%, but if I start rotating it this way, then I'm going to go and be slightly larger, etc. And then I can continue rotating this triangle as I go along from tap to tap to tap, which is going to go and make this triangle larger, 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 but at no point will it ever get greater than a 1:2 ratio. If I would continue to rotate this through the taps, eventually I would come to a point where my secondary tap would be the same as my primary. It does have some inherent disadvantages. First of all, you're going to need to have a larger kVA rating than what you would for a Y-connected autotransformer. Just due to the way that a Delta Autotransformer operates, we are going to go and have to transform all of our values of voltage. We never can conduct anything directly, whereas our Y, we're able to do a little bit of direct conduction. But it does have an advantage in that when we're dealing with 3-phase loads, it is going to be completely free from harmonic values of voltage. They show you a little diagram just showing what the ratios are going to look like over here. The 2:1 ratio where they've got it connected directly across the high voltage to the secondary, smaller voltage, the low voltage. And then they show that as they rotate that triangle through, once again, they're going to be able to achieve other transformation ratios. But those other transformation ratios are always going to be limited to never more than 2:1 type of transformation. The next one that we're going to look at is a very common one. This is called the open delta connection. The open delta connection is basically where we are going to grow a triangle. Rather than rotating a triangle through the way that we did on the Delta Autotransformer, the Delta Autotransformer has always got some issues, by the way, to do with the fact that it is going to have differing phase values inside of it, or differing phase angles that are going to be inside of it. It's never going to match fully. And as I rotate that triangle through the inside of the Delta Autotransformer, it's always kind of changing where those different phases are going to be at, where it's A phase, B phase, C phase, because that triangle is rotating through on the inside over there. Off of the open Delta Autotransformer, we get this advantage in that we are just taking a triangle and we're starting with that triangle up here in this corner basically, and we're just making this triangle bigger and bigger and bigger by attaching across different sets of taps. And what that's going to allow us to do is that's going to allow us to maintain our A, B, and C phases in the proper order. It also does require one less winding, so I don't need a winding across there, and it requires one less tap one less tap to go and change, because I don't have to change 3 lines at once. I only have to change 2 lines at once. And all of this stuff starts to really add up when you're looking at cost of a piece of equipment. What it allows us to do is it allows us to go and feed in power, my red line, my black line, my blue line over here, and then we are able to go and feed out of this at differing values of voltage out to my actual motors that I'm going to go and have on here. The one thing I do want to note is that one of my lines is connected directly across over here. So one of these lines is always going to be floating a little bit above ground. If we're dealing with a delta, remember that neutral does exist theoretically in the middle of any sort of a triangle. So this line over here, the one that goes and carries directly through, is always going to be floating a certain distance above that inherent neutral that exists over there. We don't have a neutral, but we know that the voltages are balanced around it. Which means that we will have a slightly different, anytime that we're using this, we're going to go and have a slightly different voltage strain on the windings that we're going to go and have. And for our B, in this case, because that's the one that we're conducting through, we'll always have a little bit more stress. So it's more common with these that you are going to go and have one winding that can fail separately than the others, just due to the fact that it's always underneath a higher potential value of voltage. These other ones are going to be closer to the neutral. If you take a look actually at where the 65% tap is, how close that is into the neutral, that means that those windings, the red one and the blue one right now, don't see a lot of voltage stress. Very compact, very common to go and use these when we are doing autotransformer starts. That being said, autotransformation starting, whether using these, using the deltas, or using the full Y autotransformers, is becoming less and less due to VFDs. Really, we will only use a lot of our transformers starting on gigantic motors, where it would just be impractical to try to build a VFD that's going to be suitable for thousands and thousands of amps. Then we'll use the auto transformers. But in smaller and mid-size operations, electronics are taking over. The next one that we have is going to be what we refer to as the extended delta, and it kind of looks like a baby between a Y and a delta. What we have off of the extended delta is we're able to go to a higher value of voltage, that we can go our higher ratio. Remember that on our delta, we could go no larger than a 2:1. This one over here, now we're going to be able to go and feed in higher values of voltage. I'll draw all the high ones as red over here. And then we're going to be able to feed out at smaller values over here. This one is not generally going to be one where we're going to change the taps. It's going to be a fixed value of taps, because as soon as we would try to change taps, we would have to be changing all the transformer taps at the same time. We'll use it as an auto transformer, but we're not generally going to go and use it as a variable one, where we're going to go and change them on the fly in the same way that we would do for like an open delta or for some of our Y type of starters. The last one that we're going to go and take a look at is this funky beast over here, which is going to be called the Zigzag Autotransformer connection. And it is a specialized connection where I'm going to be using my windings that are going to be in opposition to each other. Remember that when we were looking at stuff, we said that the ones were the tails and the twos were the heads. So over here, I see that I've got from my A phase, the 1 and the 2. Now my A phase is actually split. It doesn't just have X1, X2, it's actually got X3 and X4. And X3 and X4 are going to follow the same convention, that my even numbers are going to be the heads. So here I find my other A winding, and it is going to go and look like that. So I've got my A winding that is split apart and is going across two of these. My B winding is going to be done the exact same way. Here's an even number on the B, so it's got a head. Here's an even number on the B, so it's going to go and have a arrowhead. And then my C, done the same way. Even number gets an arrowhead. Even number gets a arrowhead. And what you'll note about this is we get this really cool thing happening, where we have got 3 arrowheads pointing in, as well as we've got 3 arrowheads that are pointing back out of this. Which means that we're going to go and work out to having some cancellations inside of here. And we're going to talk about that here in a second. What this does is this goes and provides a neutral, where I would not normally otherwise have a neutral. So if I've got a delta connected secondary system, I can go and create a 3-phase 4-wire system. What you cannot do is you cannot go and just start throwing transformers, Ys and deltas together on the same system without properly looking at them in engineering, because you can result in some serious line-to-line types of shorts. If I've got a delta system, let's say I've got a delta bus over here, and I want to go and connect some single-phase loads, or I have some single-phase loads that sometimes do exist on there, just transient loads or something. What I'll do is I'll go and place one of these across here. Now, what they are showing you right now, you'll note that everything over here is X's. What they're showing you right now is they are showing you that this is a zigzag filter right now, okay? I'm just going to go and put that up in big letters, filter. Okay, because this is actually being used to go and filter out well, in a lot of cases, third harmonics, as well as it's going to allow me to go and filter any sort of implied neutral currents out of this system. It is not for transformation, this one. We've got 2 different zigzag connections. We've got zigzag filters, which are just going to be 2 sets of windings like this that we're going to go and connect across our lines, our A line, our B line, and our C line. And they're going to allow us to go and, even though it's not a delta, see, this is how the delta triangle would normally look. Even though it's not a delta, it would allow us to go and create a neutral point inside of the very center over here. And normally we wouldn't get a lot of current that would flow through these. So this one is a filter. not a transformation. We'll sometimes hear them referred to as zero sequence filters. The Canadian Electrical Code actually never says zigzag transformer inside. Actually, it does. It does it in one point in the back there. But for the rest, it refers to them as zero sequence filters. And they're going to be specially wound in a lot of cases as well. Excuse me. If I have got a delta system where I've got a bunch of variable frequency drives, or it could be soft starts or anything else that's going to be harmonic starts, we're oftentimes going to go and receive a lot of harmonic distortion off of there. The THD, or total harmonic distortion, levels will be high, and as a result of that, I need to go and find some way to go and filter them out. So I can connect one of these units, the filtering unit, across there, and then that is going to allow me to go and create a neutral connection that I can then go and take any of those harmonics in on, and the harmonics are actually going to be able to go and cancel themselves out. Normally, the Zigzag Autotransformer doesn't actually go and carry any current. Remember, it's not a transformer, it's just a filter. It's just going to have a small amount of magnetic flux that's going to be going through it. But as soon as there is either unbalanced load, something coming in on the neutral, or harmonics, then it is going to go and take that and it's going to divide it across the 3 lines. And over here, I see that I would be dividing it into heading into these arrowheads, and then I'm going to be heading out. So if we take a look at the C phase, I'm heading into this line at the same time as I'm going to have another current that's going to be equal magnitude that's going to be heading out. Well, if we've got 2 equal values of current, one heading in and one heading out, we know that their flux is going to go and cancel each other out. This connection that they're showing over here, once again, is going to be the zigzag filter that we're looking at. We're filtering this thing out. And it is going to go and have this neutral connection over here where we're going to go and take in any unbalanced neutral current. So we get some single phase loads on there. Those single phase loads are going to deliver current in here. And then because all 3 of these lines are equal and canceling, it's going to see them all as having an equal value of impedance. And therefore, the current is going to split evenly into each one of them. And as that current goes through, you can use your left-hand rule over here. You can see that this is going to be creating a phase, or a flux that's going to be going that direction, while at the same time, the current that feeds into here travels through and travels through up to here, and is going to go and create a current that is going to be going in the opposite direction. Or sorry, not a current, but a flux in the opposite direction, which means that we get a net of 0 flux. 0 flux. I cannot write this morning. 0 flux that we are going to go and have out of them. It's going to take the neutral current, equally divide it up, and ultimately what happens is it's going to go and send that current out to the lines in a balanced manner. No matter what size this neutral current is, or no matter what phase angle that neutral current comes in on, it is going to split it up. So if I had 17 amps, it would go and split that 17 amps up equally and put it out onto each of my lines equally, which is what keeps my entire system then in balance. This is also able to go and supply some single phase loads. If I do want to go and throw a couple of single phase loads onto a delta system, let's say that I had a big delta motor system, and then all of a sudden somebody's like, hey, we're going to put a site trailer over here at the far side of this industrial yard, and we just want to throw in, just a heater and a couple lights, and we need a place for the guys to plug in their coffee maker and their computer, etc. We could tap in one of these, and when we place one of these across there, we'd have that neutral connection. The neutral connection would then be allowing us to go and take for our single phase loads. We could just drop a single phase panel somewhere. We'll just draw one out. We could drop a single phase panel, and I could go and feed in from my one line. I could feed in from my other line, and I could feed in from my neutral that I've created with the zigzag into that panel. And then from that panel, I would then be able to distribute out to the individual loads that I have inside there. I take current in from one of these lines over here. It's going to go through my single phase loads, come back onto the neutral, and then it is going to get split up and sent back onto my lines evenly, which is going to go and prevent me from overloading just a single phase at a time. Once again, I do want to go and point out that this is a filter that we have over here. This is not a actual transformation going down from high to low. We do have zigzag auto transformers where we will sometimes place them in, not as a filter on an existing delta, but where I can place them in as just my brand new initial install of a transformer. In that case, I'm going to go and have one more set of windings that are going to be wound on them. I'm going to have some primary windings that are also going to be wound onto these beasts and tied together in a wire delta. But we're not going to worry too much about that. Do I want you to stress much over the complications of it? No. To be honest, I'm skimming this subject over here on the Zigzag Autotransformer. If we have time, we can definitely go into in depth, but it's going to be about 2 hours of, we actually have to go into the vectors intensively in order to completely explain what's going on inside of these. Are you going to do that in the field? Absolutely not. What you're going to do in the field is you're going to go and say, hey, I need a Zigzag Autotransformer. I've got this issue with, some weird harmonics coming off my 3-phase loads, and I want to be able to filter them out. And so you are just going to go and get a KVA spec, and the transformer is going to go and come with a B and C labeled on it, as well as a big N, and you're going to make those connections as is. So don't stress too much about this one. A lot of people just kind of get real hung up on the Zigzag because they go, but that thing, I don't get it. Why is it doing the thing that it's doing? Well, it's all doing the thing it's doing because it's straight up electrical theory, but it's not something that you need to be able to go and understand the inside. You have to be able to go and describe. If you go back to what the actual goal is of the ITA learning guide, is to be able to identify and describe the Zigzag Autotransformer. Can you identify it? Absolutely. It has got countering windings, and it has got a phasor diagram that looks like, let me just get this eraser out over here, that looks like this thing over here. That's how you're going to go and identify it. You're also going to identify it off the fact that it's called a zero sequence filter at times. Can you describe it? Yeah, it's placed onto a delta system, and it gives us a neutral where we otherwise wouldn't have a neutral, which allows us to filter out harmonics. And that's about as much as you need to know on these.